This is the 8th video in my series on three-phase power transformers. In this video, I'll be looking at Y delta connections, to be more specific, the current flows in Y delta connected three-phase transformers. You can find out more on this subject in my course entitled Electrical Three-Phase Power Transformer Fundamentals. You can access this and my other courses on my Stan Store at this web address. Let's look at the currents now in this transformer. And in order to look at the currents, of course, we have to add a load, and I've chosen a delta load. I could have just as easily chosen a Y load. It's not going to make that much difference to the flow of the secondary or the primary currents for that matter. And I've chosen a resistive load because I don't want any phase shifting going on due to the load itself. Certainly it will add to the shifting if there is any, but that isn't what we're looking at right now. So let's just assume that the load is purely resistive. I've also drawn in the voltage phasors in miniature up near the title there, just so we can keep track of them. Now, I've adopted the same standard pretty much that I did with the voltages, but keep in mind now we're looking at currents. So all the currents that are associated with what we're going to look at on the primary side, I'm going to use capital letters or uppercase letters. And on the secondary side, I will be using the lowercase letters. The line currents, I'm going to title them as I line R primary, I line white primary, and I line blue primary. You'll notice that I've capitalized the R prime and the W prime and the B prime to indicate that that is the primary side that we're talking about. And I'm going to do a similar thing on the secondary. The lines coming off of the transformer, I'm going to call I line with lowercase r secondary and a lowercase w secondary and a lowercase blue secondary. The transformer primary winding current I'm going to refer to with a capital R. And the current coming in the line is going to flow down and into the spot of that red transformer. And all of the current flowing through the red phase coil or winding of the transformer is going to be equal to I line R primed in a Y delta connected transformer. Similarly, the current flowing in the winding of the primary white transformer is going to flow into the spot on that transformer from the I line W prime, and the same thing is it's going to be equal to the line current, and similarly the blue phase is going to be designated B, and it's going to be equal to the line current on the blue phase line coming in. That is because we have a Y connected primary. Now on the secondary winding of the transformer, I'm going to call the current flowing in that winding as lowercase r. And in the case of a lowercase r and the current flowing in this transformer, because the current is flowing into a spot on the primary, it's going to flow out of the spot on the secondary. And similarly, the white phase secondary current coil is going to flow out of the spot, and the blue phase current coil is going to flow out of the spot. Now, we would like to find out what the current is that's flowing in the I line R secondary or R sec, W sec, and B sec, and we're going to have a look at that right now. I would now like to figure out what the currents are that are flowing in the line to the load. And I'm going to start with the red phase line secondary current. And if you go back to the transformer, you'll see it's connected in two places. It's connected to the X1 terminal of the red transformer and is connected to the X2 terminal of the blue phase transformer. What that means is the current that's flowing in the line is going to be made up of the red phase current, but the current, we have to subtract the current that's flowing into the blue phase because it's flowing out of the line. So we have to subtract the blue phase current, and we know what the plus blue phase current is. The minus blue phase current is just 180 degrees from that. So these are the two phasors that make up the line current. So all we need to do is connect them, and that will be the current that's flowing in the secondary of the line of the red phase. The delta-connected secondary currents form a triangle of three equal sides, which is an equilateral triangle, and the contained angles are 60 degrees. So in trying to come up with the angle between the red phase and the minus blue phase, if we move the minus blue phase over, it forms a straight line with the plus blue phase. And if we subtract 60 degrees from 180 degrees, which the straight line forms, then we're left with 120 degrees. And that is the contained angle between the red phase and the minus blue phase current. Now the triangle formed by the red and minus blue phase currents and the I line R secondary current, it is an isosceles triangle. So the two sides that are equal will share the 60 degrees that are left over when you subtract 120 from 180, and we're left with 30 degrees. So that's just a quick breeze of trigonometry there, just to prove that we have a triangle with two contained angles of 30 degrees and one of 120 degrees. If we move I line R secondary up to compare it to the primary side of the transformer, we know that the red phase primary current flowing in the primary side of the transformer is equal to the line current coming in. So we can see that the I line R secondary will lag the I line R primary by 30 degrees. Or in generally speaking, we'll say that the secondary lags the primary by 30 degrees. Because we've just done the investigation for just one line, the I line R secondary. However, we can go through the same exercise for the white phase and the blue phase, and we'll come up with the same thing, that the line currents of the secondary lag the line currents of the primary by 30 degrees. And that is not necessarily too difficult to think about, because we already saw that the line-to-line voltages lag the primary line-to-line voltages or phase-to-phase voltages by 30 degrees, and we just added a resistance load, so the current should be lagging by 30 degrees as well. In my next video, I'll be looking at the magnitudes of the current flows in a wide delta connected transformer. However, I've run out of time in this video, so be sure to stay tuned to my next video where you'll discover the magnitudes of the current flows. As I said before, you can find out more on this subject in my course entitled Electrical Three-Phase Power Transformer Fundamentals. You can access this and my other courses on my Stan Store at this web address. This video is part of my Electrical Technical Information series. In this series, I'll be covering essential topics to help you understand electrical systems. Be sure and stay tuned, as I will also from time to time be reviewing electrical products that, in my opinion, are worthy of paying attention to. Some of those products include 𝐃𝐈𝐒𝐂𝐋𝐀𝐈𝐿 big and small standby generators. This is the best time to try out any of 𝐃𝐈𝐒𝐂 products because they are having a huge sale starting on April the 4th and lasting until April 21st. Here are just a few of their products, starting with the 𝐃𝐈𝐒𝐂 Delta Pro Ultra, including the River line of smaller standby generators. And a range of portable solar panels. And finally, a unique product, the Wave 2, which is a portable air conditioner / heater. As I said, this is the best time to try out any of 𝐃𝐈𝐒𝐂's products because it is having a huge sale starting April the 4th and lasting until April 21st. During this time, you can experience huge savings off the original market price. To obtain more information on this subject and pick up your free digital copy of the Ultimate Guide to Residential Standby Generators, simply fill out the information requested when you go to this website, https://lowercase bit.ly/4/4D_X77. Before I end this video, I want to repeat the connection to obtain my free copy of the Ultimate Guide to Residential Standby Generators and receive access to the major April sales on many of the 𝐃𝐈𝐒𝐂 products. Also, here is a connection to obtain a free copy of my 50-page electrical power crib sheets. And finally, here is the link to all of my electrical courses, which are located in my Stan Store.